Welcome again to another video of the power quality. In this video, we talk about the two-wire passive compensator. What should be the value of the BC or the compensator so that the power factor at the load end and VL and IC can be in same phase. So just to recap, this is the VS and IS are the supply voltage and the current. RS is the load transmission line resistance, and LS is the inductance of the transmission line. The load is usually the impedance written as Z. However, we are writing this as the admittance Y, and we know that Y is equal to 1 by Z, so we can replace this R plus JXL in the denominator. We can multiply both on top and the bottom, R minus JXL and R minus JXL, and we can rewrite this in terms of G and B, where G is the conductance and B is the susceptance. And together this admittance Y, if we multiply with this V supply voltage, we get the value of the current. Now what's the total impedance is the sum of these two, right? So if these two are in series, so this like R plus J XL will be the impedance of here. And since these two are in parallel and both are represented as Y1 and Y2 admittance, so we just need to add these two. And 1 by admittance will be the Z, and this will be added with this term and this term. So there will be addition of three terms, 1, 2, and 3. Again, this is the admittance Y1 and our admittance Y2. In parallel, we need to add these two, Y1 and Y2. We will add these two. And to get the impedance 1 by Y1 plus Y2, addition of this with this L and R. So keeping these two in the same frame, we can write this as the imaginary part of this term if we'll make it 0. And we consider here the BT. BT is nothing but because these two are added up, so minus of JBL and JBC are added up, and that becomes BT. BT is minus of JBL and BC. So now we have here the three terms, and these three terms what we have just discussed. So to get, let us enlarge this. So this is that power factor correction at the load terminal. So imaginary part is to be 0. So this term is multiplied with here, and it's taken out here, and we get the multiplication of these two terms over here. Then we get a multiplication of these two terms over here. Thus we get all the non-imaginary terms like these two imaginary and this one. So it will be non-imaginary term in one end, and then we can take the imaginary term J, like when we multiply X with GL, or when BT is multiplied with RS. So these imaginary terms will be one end, and at the bottom we have got these terms over here. So if we multiply this complex conjugate in both the top and the bottom, so the bottom part, it will be a square terms, and at the top we'll have this GL term is multiplied with all those things. What I am interested for is the imaginary part. So there will be a real part, and the imaginary part will have a J term. So if GL is multiplied with this imaginary part, it will be imaginary number, and BT when multiplied with this one, that will also be imaginary number. So rather than taking out all the discussions, so we will have only this imaginary number, that is GL multiplied with this term, and BT multiplied with these three terms, right? So we'll have the imaginary term here, and we're less important of this. This is not of importance. This is not of importance here. Only the imaginary term over here. So the imaginary term is rewritten here with the GL square XS, then GL and this, and here we find that they cancel each other, and what we finally get is this second order equation if we take the variable as bt. So the value of bt is expressed minus b plus minus root over of b square minus 4ac by 2a. So minus b is minus 1, that is 1, and we have root over of b square, that is 1 square, minus 4a, and a means this and c is this. So in this way we get the value of bt. Also we can have a discussion on that zero voltage regulation. Suppose instead of having a zero power factor correction, so if you have a power factor correction, the value of bc chosen will be in this way, right? So but if we have a zero voltage regulation, then what is the condition is that? Condition is simple, that the magnitude of the VL must be equal to the magnitude of VS. So like is magnitude of Vs. So in this case, if these two are equal, so these cancel each other, what we get is that this term should be equals to 1, which is here. So this term should be equals to 1. Sorry. So if we rewrite this, that means if we multiply this term with this one and this term will take it up, so this term will cancel each other. So what we get is that this big term, so this big term will be, it should be equals to 1, and then when we solve it, like take a square of both the sides, we get this, and then we evaluate it. Like this is a 3-term square, then you have a 2-term square, then you take 3-term square is like 3-term squares, and 2ab, 2bc, 2ca. Here 2-term square, so we have got 1, 2, 3 terms over here. So good thing is that a lot of things get cancel each other here. 1 and 1, this also cancel each other, and what we get is that we get a second order equation in terms of when the variable is bt. So taking to easy it out, x square plus rs square, let us say this is a. Now this equation looks very simple. If a is multiplied with bt and x squared, this is x, and this is a constant, and what we get finally, the value of the bt here in terms of a. So here the a is we divided this by a, the 2 get cancelled out. So this is the bt value for voltage regulation, and this is another for power factor correction, the bt value is this. So this is how we can distinguish between the bt value for the zero voltage regulation and power factor correction. So thank you very much.